Okay, so here we have a question looking at the size of a virus, the Ebola virus. And we're going to use some scientific notation to understand it, and we're also going to look at this in standard form. So in part A, what do they tell us? Well, they tell us that, well, first of all, in the heading here, that the Ebola virus has an average length between 974 and 1086 nanometers. We're told in part A that each nanometer, so 1 nanometer, equals what? Well, it equals 1 billionth of a meter, or 1 times 10 to the negative ninth meters. We want to write 1 nanometer in standard form. So we're just going to take this, write this number, and write it in standard form. So I'm assuming they want us to write this in meters, right? So we have 1 times 10 to the negative ninth, and that means take the number 1 and divide it by 10 9 times. Every time you divide by 10, your number will have its decimal move once to the left. So with the number 1, right, we have our decimal as 1.0. So I'll write 1 right here. 1.0. And that's in meters. Well, divide by 10, we move to the left. Do this over and over again, and what we'll have is 8 zeros, right? Not 9 zeros, because our first hop is over that 1. So we have 8 zeros. 4, 8. And that's 1 nanometer, right, in standard form, written in meters. Okay. In part B, we want to write the smaller size measurement of an Ebola virus, which is 974 nanometers in standard form and scientific notation. So here I'm assuming, again, they want us to write this in meters, right? Because 974 nanometers, that's already, right, that's already in standard form. We just want to write this in meters. So here's 1 nanometer written in standard form with meters. Well, 2 nanometers, of course, would give us the same thing, but with a 2. And we keep going until we reach 10 nanometers. Now, 10 nanometers looks just like this. Same idea, 1 less 0. What's happening here, of course, is that we're moving up in place value, right? 10 is 10 times larger than 1. And you might have a hard time seeing why this makes sense. Forget all the zeros for a moment. Imagine here we just have a 1. Well, 10 would look just like this, right? 1 and then 10. The same thing's happening here, but on a scale that's much smaller. Here we have a 1, and then we have the same thing, but 7 zeros and a 1, and we could put a 0 after to see what's happening. And notice how it looks like going from 1 to 10. The same idea as when we do count from 1 to 10. 100, of course, would then follow the same pattern, right? 100 is 10 times greater than 10. So it has 1 less 0, a 1, and then you could put 2 zeros after it just to envision how we have this pattern. 1, 10, 100. You can see it. Now 974 of nanometers, of course, we're writing in meters, will just be the same idea as 100, but with a 974, right? That's what this looks like as a nanometer in standard form, 974 nanometers, if we write them in meters. So now, how would this be in scientific notation? Well, not 9.74, we'd want a number between 1 and 10, times 10 to what? Well, in order to get 9.74 from this number, we have to multiply by 10 once, twice, 3, 4, 5, 6, 7 times. We have to multiply 7 powers of 10. But that would change the value of the number. We don't want to do that. So we balance it by dividing by 7 powers of 10. In other words, take it 9.74 times 10 to the negative 7th. That balances it out really nicely. Okay, in C, we want to write the larger size measurement in standard form and scientific notation. That's for B. For C, our largest number is 1086. Well, if I follow this pattern, 1, 10, 100, 1,000 should be in the next place value up, right? So we should have 1 less 0 than we did with the hundreds. So now we have 5 zeros, and you can picture this as 1,000 almost, right? You follow 1,000, 100, 10, and 1. You can see how that might make sense. So that's 1,000 nanometers written in meters, but we want to write that in scientific notation. So to write 1,086, I would just add an 8 and a 6 right here, 1,086, and now I can write it in scientific notation, 1.086, a number between 1 and 10, times 10 to what power? Well, we had to move the decimal from 3, 4, 5, 6 places to the right just to make this number between 1 and 10. So we balanced that by dividing by 10 6 times for the same reasons as before. There's always that balance of multiplication and division. So that's written in standard form right here and scientific notation right here. Last we have D, which says 1 micrometer, and we should write 1 micrometer like this with that U shape, is equal to 1/1,000,000th of a meter, or 1 times 10 to the negative 6th of a meter. Do any Ebola viruses reach 1 micrometer? Explain why your answer makes sense. Well, the answer is yes, and you can see it right here. If we compare these two numbers in scientific notation, right? A micrometer and the larger range size of the Ebola viruses in over 1,000 nanometers do have the same power of 10 to the negative 6th. So you could actually say some of the larger Ebola viruses are a little over 1 micrometer. And you can see that in the powers of 10, but you might also say that the reason this makes sense, if we look at the size of the larger Ebola viruses, they're not 1 nanometer, they're 1,000 nanometers. And in fact, the structure of a nanometer, 1 times 10 to the negative 9th meters, right? If we take that and multiply it by 10 to the 3, in other words, if we take 1,000 nanometers, or multiply this, what's going to happen? Well, if I multiply 10 to the 3rd by 10 to the negative 9th, I get 10 to the negative 6th. Laws of exponents right there. So every 1,000 nanometers you have 1 micrometer. And that makes sense. Look at the names of nanometers. They're 1/1000,000th. And micrometers 1/1,000,000th. If you have 1,000 1/1000ths, that makes 1/1,000,000th. And the reverse is true when you're on the other side of your decimals over there, and you're dealing with powers of 10 that are larger than 1. 1,000,000, take 1,000 millions and you get a billion. It's the reversal there. So on the smaller side, the billionth is the smaller number, but on the larger side, a billionth is larger. And the gap between them is always 10 to the 3rd. In fact, you'll notice a lot of the name structure in our number system, going from a million to a billion to a trillion. Going from 1,000 to a million to a billion, up to a trillion, a quadrillion, and so forth. Every time you jump up by 1,000, or multiply by 1,000, or divide by 1,000, you're going to change the name structure of your measurement. And that's how the name structure is generally set up, so that every 1,000, every 3 powers of 10 that you multiply by, you get a new name. All right, so I hope this helped a little bit. Thanks.